The competition this year for 118 is the Slug Madness. So they have the field, the stripes, 3-point line, slam dunk line, so 3-point, free throw, slam dunk, and 3 milk. Yeah, I'll put that back in a second. Remote pointer. Yeah, and then they've got the IR transmitters are back here on the backboards. So if you look at this from the side, it's a milk crate, 13 inches. This is the open side. And there's a backboard, what is it, 18 inches tall? You guys remember? Yeah. And then the IR beacon pokes through 3 inches above. Yeah. And so you can slam dunk, you can shoot from 3, so it's 1 point, 2 points, and 3 points.
Half a point.
Half a point?
1 point, 2 points, 3 points. If they're all the way up against the wall.
So half a point up here. 1 point where? Anywhere in here or?
1 point in between.
In between. 1 point. Got it. Okay. Yes, this is done for certain robots from last year. Won't work this year. All right. So this is that's the scoring and the. It's interesting actually. This one is exceptionally challenging for the following. So each year we have sort of a different thing that makes it hard. This year, what makes it hard is the fact that you have to arc in. You can't fire. You can't fire in at high velocity. Doesn't work. All right. It just bounces right. I mean, you can, but. Well, so yeah, actually, if you fire at high velocity from the top of your robot and you put sufficient backspin on it, you can actually get it to hit and bounce in. But that's challenging, and it's really challenging to do at two different distances. All right.
If you're firing ping pong balls and you put spin on it, it's going to drift. They're
going to drift a lot. Which is the other thing you can do is you can actually put a hell of a lot of top spin on your ping pong ball, and they actually do take a curving trajectory. And in fact, if you've ever played someone who's good in ping pong, they sort of wait for the ball to fall off the end of the table so that they can hit it from about 2 feet, above the ground, traveling upwards. And when they do this, the ball comes back over, and it looks like it's behaving perfectly normally for about the first 4 feet of its trajectory, right? And you get in the right spot, and they go funk right in front of you, and you're like, okay, how did that happen? And the worst is when it hits the table, it accelerates, because it's got so much topspin that it actually hits the table and imparts that angular momentum goes away and it becomes linear velocity, and so it hits and skips very low. Well, actually the physics of ping pong balls are quite spectacular. There's whole fun topics on what you can do with a ping pong ball, and
there's a video on YouTube of a wiffle ball player.
Yes.
Similar thing.
Now, a wiffle ball is actually, the physics behind a wiffle ball are phenomenal, so everyone knows what a wiffle ball is, right? Have you seen what the holes look like? They're not symmetric. There's an equator, sort of on the wiffle, and there are 4 small holes in the top and 8 big oblong holes across the bottom. And actually, the secret, apparently it took him 5 years of taking hollow plastic spheres and drilling holes in them and throwing them to figure out what worked well. All right? And then it took computational fluid dynamicists another 20 years to figure out why it actually works. All right? Because the airflow around and through this thing is ridiculously complicated. And there's all kinds of eddy vortices going on, and there's the thing that helps, of course, is that the mass of the ball is very light. Which is, you could do this, and if you sort of made it out of milled titanium, it pretty much doesn't matter what holes you put in it. It goes straight. Okay. In other words, it only works because what you're doing is you're manipulating the aerodynamic forces along this while it's spinning, and the aerodynamic forces on it are proportional to velocity squared. And the best Major League Baseball player who could be the fastest throw in the league, I think, is 110 miles an hour. It's not that fast. All right. Not in aerodynamic terms, right? 747 flies at 600 miles an hour, all right? So you don't get a whole lot of force, so it's got to be light in order to make it work, and so that's why wiffle ball works. No, actually, the reason he invented the wiffle ball is kind of a funny story, but the reason he did it was because his son kept breaking windows, in the local neighborhood with a regular baseball. And so he wanted something that he could play with that wouldn't actually shatter the windows of all the neighbors' houses because he got tired of paying for broken windows. So, what's that? Could have given him a ping pong ball, but he wanted him to play baseball. And it turns out to have been a huge success, by the way. The wiffle ball's kind of interesting. Anyway, all right. So, where were we last time? So first of all, before I launch any questions, you're all here, so that means there's got to be a reason you're here. No? No questions whatsoever. Huh? What's that? Nothing better to do. Okay. The review tomorrow is at 6 p.m. Yeah. So in E2, all right. Yes, shockingly, actually, because this one's on a Wednesday, not on a Friday. All right.
Right. When is the midterm and where?
And the midterm, if you look on, I put it on top of your homework, but the midterm, once again, is Kresge 327 at noon. What's that? Same time, different room. It's a much, much bigger room. It'll allow you guys all room to spread out so you can, bring all of your books and everything else. Normal open book, open notes, no MATLAB, no calculator that can imitate MATLAB. All right. So, just, the most complicated thing you're going to do with the calculator is take an arctangent. All right. Yeah, bring a calculator. You might also want to bring a ruler because there's going to be certain things I might ask you to do graphically where having a ruler will help you sort of draw things to scale and measure it out, which would be easier than if you want a protractor, it wouldn't hurt you. It's not going to help you all that much, but it might help for drawing angles correctly, but it's not going to make that big a difference. You've seen how I draw angles in here. I mean, what I present is more or less what I want. Okay, so if as long as you have it, I don't care that it looks like it's going off at 135, and you write that this is actually 167. Okay, what's that? Sure, it can be 92. As long as you've labeled it correctly, and it's going up, that's okay. All right, so but approximate is fine. All right, which means angles wind up looking suspiciously like 45 all the time. But anyway, it's one of the tricks they teach you in quals. Is never draw your angles at 45 degrees, because then you can't tell the sine from the cosine. Right, so you say, well, we've got a mass and it's on a slope, and so the thrust is, which one is the sine, which one's the cosine, right? Whereas if you just draw it at 30 degrees, right, you say, okay, so here's my slope, here's my mass. Okay, now I know, right? It's remarkable how silly a trick it is not to draw it at 45, and how many times you trap yourself by drawing a 45 and staring at it, and then actually think about which one's the sine, which one's the cosine. Whereas if you do this, you just look. Right, okay. All right, so we were at our last spot. We were starting to do the zero angle root locus. All right, so we've done regular root locus. Now we've done zero angle root locus. So the whole thing with zero angle root locus is I've got, instead of negative feedback, all right, I'm actually looking at positive feedback, and what I do to make my life easy is I just take that and move it into the K that I use. So this allows me to draw the root locus to analyze where the roots are for the entire range of Ks, plus infinity to minus infinity, and everything in between. All right, and where are they when K is 0, by the way? Yeah, if K is 0, where are they? Where are the closed loop poles of the system when K is 0? In the open loop, right? At the open loop poles. Okay, this is sort of important, right? It starts from the open loop, it goes to the closed loop. In both cases, it goes from the poles to the zeros.
But if you have no gain at all, gain is, never mind, sorry. I just thought everything was being shut to 0 for that time.
No, it's not. All right. So, okay. So we have the first rule applies, which is that you go from the poles to the zeros, from the open loop poles to the open loop zeros. You're just going to take a different path there than you took in the 180 degree root locus. what we do is we take the logical knot of the real axis from the 180. All right. So you can write this as to the left of an even number where 0 is even, or the easier one to do is, hey, not where it's to the left of an odd number. All right. That's the sort of easiest one because you always start out drawing the 181 first anyway. So you draw the 181 first, figure out what's on the real axis. For the 0 angle, it's just where it wasn't, it is. Where it is, it isn't. I think, yeah. The center of the asymptotes is in exactly the same place. Nothing has changed. The angle is, instead of this being plus or minus, being minus 180, this is now at 0. All right? Or you could put it at 360. It doesn't really matter. It's the same angle. All right? Now, if you do this by the formula, you have to remember the formula switches. If you do this by putting a, you say, look, here's my real, here's my axis, and when I zoom out to 30,000 feet from here, this looks like however number of poles I have at minus alpha, right? I've taken what was a complicated pole 0 map and done it, so now it looks like 1 over s minus alpha, or I guess s plus alpha, to the excess number of poles over zeros, right? And if I look at this and I draw a circle somewhere out far away, right, and it's got to be on the root locus, well, all that is, right, is I say, okay, well, here's my asymptote angle, right? So minus 3 of them, because I got 3 poles here at minus alpha, right? There's no zeros, because I've gotten rid of all of those, right? Is going to equal to minus 180. And if I want plus the L minus 1 modulo 360, right, times 360. So now I say, well, hey, that's great. So for the minus 180, that means there's the first one. Is at 60 degrees, and I know it's right. So this is when I'm doing the 180 degree root locus. When I'm doing the 0 degree root locus, I just say, hey, no problem. 0. Right? I just changed the 180 to a 0 because now I'm looking for 0 degrees of phase rather than 180 degrees of phase. Right? It just points the other way. So now I've got one here like that. Okay? So that's the 0 degrees, and the other one is in the, and this one is in there. All right? So this is 180, and that's 0 degrees. So as long as I sort of remember what I'm doing, then I don't need to remember the formula. If you want to remember the formula, that's fine. I don't particularly care. It's up to you. Same thing for departure and arrival angles. Again, now I'm looking for 0 degrees of phase instead of 180. Symmetry still applies in all cases, and the breakouts and the break-ins haven't changed from before. And as I said, this is moderately useful. It's only useful in relatively few situations where you're not trying to factor a cubic. Yeah.
Can you get false answers from that?
From the breakout and the break-in? This is a necessary but not sufficient condition. So you will get, all of the roots that you get here will be roots where there is a multiplicity of roots on top of the root locus that come together. Okay? All of the answers you get. However, some of them will be trivial ones, like if they're on top of each other to begin with and they split from there, you'll get that location back. Okay? Other ones will be for the 0 angle, other ones will be from the 180. Okay? And so you just have to figure out which one applies where. All right, so it does require a first order kind of back of the envelope sketch to figure out where the hell I'm looking. And then once I know, okay, now I can go ahead and apply these. All right, so we did a couple of examples. They all seem to work just fine. And now we started talking about various forms of compensators. All right, so let's start. I'll do that on this side and start a new one. Okay, so what we're going to get to is a sort of a recipe. Let me back up a step and go philosophically. Okay, so we now have some great tools. Okay, they work really well. They're pretty easy to do, and I can take a differential equation and in a matter of seconds now write down what the Laplace transform of that is, solve for the initial conditions or just the transfer function for the input as I'm looking for it. take that. I know how to look at the characteristic equation of that. I know how to wrap it into feedback, and I know now how to factor that polynomial to figure out what is the transient response going to look like based on where the locations of those roots are. I know how to take time domain specifications and move them into the S-plane to say where are the acceptable place where I want to put all my roots to get that kind of compensation. All of this works, and it works fine. Now, the big thing is, so we are sort of almost all the way through analysis at this point. There really is no analysis left, and we are now entering in design. Okay? So the design is, what we've done in the past is we said, look, assume a compensator of this form, and now solve for all the coefficients to find out what you're doing. Now, what we're going to start saying is, well, wait a minute, what if I have something that looks like, oh, I don't know, that. Right? Here's my fairly complicated differential equation. Right? And by the way, I have lost no information. Right? I can go from this back to my differential equation. Right? Actually, there's a little bit of information lost, but not much. From the transfer function, I can definitely do it. From here, I can almost do it. I'm missing a gain, a DC gain. Right? With this and a DC gain, I have all the information I need to go all the way back to a differential equation. Ooh, that's a good problem. Anyway, I look at this and I say, okay, well, let's draw the root locus really quick for just straight gain. So I'm going to do the 180-degree root locus. I know that that's on the locus. I know that I've got 1, 2, 3, 4, 1, 2, 3, 4. I'm going to have 2 poles going to 2 of these zeros and 2 poles going to 2 of those zeros. So it doesn't go anywhere. Okay, there's no asymptotes. Everything's fine. All right, and I know based on experience, I start calculating the departure angles, and I'm going to find something. I calculate the departure angles. Let's say I find this way. These two are probably going to go in like this, meet up, split. One goes to one, the other goes the other way. If I'm lucky, this is going to do that, and that's going to do that. If I'm unlucky, this is going to do, that and that. In any case, I now have my location of all the possibilities that I have where I'm going to get where I can put the closed loop holes. Okay? And now I say, well, I don't like it. I don't like where they go. I can't meet my specs. I'm not very happy with them for whatever reason. I want to move them around. Okay? So far we've had a couple of classes of compensators that we know how to use, but basically the idea is I'm going to start putting poles and zeros down that are from my compensator as opposed to my original system, and I'm going to see how that modifies the root locus until I get a root locus that I'm happy with, pick the gain, and then I'm done. Right? So the problem is this is an infinite search space. Right? There is no methodological there's no method with a clear methodology that will tell you where to put down poles and zeros and what's a good idea, what's not, where to put them, how many of them to put, where to shove them, such that I get the response that I want. Right? And that lack of systematicness can become problematic because you start, well, I'll put them here. No, I'll put them there. And you sort of just keep guessing. And guessing is a fairly poor way of finding a good solution. So what we're going to do is develop a number of tools, a few classes of controllers that will give you a good place to start. They are not by any means the only ways to do this, nor are the only kinds of compensators that you actually build. Right? It is simply this will sort of give you a systematic way to start putting things down that will alter the root locus in ways that you desire. Right? So this is where we're going. Okay, it's to try to give you a little bit of a systematic method of doing this. Okay, so what we've got, we have our proportional that we just know. So this is proportional gain. So we've done this. We know this has the effect of increasing the spring constants in the system, making the thing a little bit more stiff and rigid. Okay. We added the next one was pure derivative control, which we put a 0 right on top of the origin, and we have KDS. All right, this is derivative, and this is the equivalent of adding a damper to the system. Okay, and this has the problem of amplifying. So this has two problems. First of all, in MATLAB this works great. In real life, this has two very, very serious problems. The first problem is, what's your DC gain? Right, your DC gain is evaluated at S equals 0. Right? What's at S equals 0? A 0. So what's your DC gain? 0. Okay? Which means you have just attenuated everything out of your DC gain of your system.
That's AC coupling?
Yeah, actually it is. It's exactly AC coupling. All right? So you have no DC gain. Your DC gain has gone to 0.
And what DC gain you want to eventually track your input?
You want to track your input. Right? So what this says when you have no DC gain is I say, okay, I'm going to inject R, right? Something I want you to track, all right? And it says, hey, I'm going to wiggle when this is wiggling, but when you stop here, instead of going here, so my system is actually going to do some tracking response and then go to 0. Right? But I didn't necessarily want it to go to 0. I wanted to go to that input. Right? I want to track my input. I can't track my input here. Right? So this is it's essentially it's a high frequency coupling. Okay. The next one we looked at was we had our integral control, which said stick a pole right at the origin. So this is Ki over S. And so the first problem you have with this is that your DC gain is 0. The second problem you have with this is that it's a derivative, which means it is going to amplify your noise, right? And the amplification of that noise is going to get higher and higher with higher frequency, which means essentially all you have is noise and nothing else. So this is going to just keep amplifying. All that will happen is you'll be swamped with high frequency noise, okay? In a pure derivative. Integral control. Now, integral control has another disadvantage, which you now know from the root locus, which is, okay, if I drop down a pole right on the origin, there's a fairly reasonable chance it's going to go the other way, right, into the right half plane fairly quickly. Right? I got to be careful with what I do because a pole right at the origin does have the great advantage of bringing my error in steady state to 0. It goes to 0. There's no question. All right, bless you. But it also tends to eat up a lot of my damping, all right, and make things a lot less stable. All right, so it's a mixed blessing, right? Yes, I can drive my error to 0, but I pay for it. I pay for it essentially by destabilizing the system. And we're going to see when we start doing Bodhi. And let me be clear. None of the stuff beyond zero angle root locus is going to be on the midterm. None of this is on the midterm. All midterm material. And I'm not even sure if I'll give you root locus. I'm trying to. Not sure if I'll give you zero angle root locus. There'll definitely be root locus problems on there. Do you like drawing? Yeah? Do you guys like this one? Well, I also made the homework kind of easy so that you could have time to study for the midterm. All right. So there are only, 3 problems on it? Something like that? Yeah. Yeah. Okay. This one's actually kind of cool, the next one. So due a week from Thursday. This one actually takes you through the design of a problem. It says, okay, try this compensation, see what happens. Try that compensation, this one happens. Bummer, there's some high-frequency oscillatory modes that you were unaware of. See what happens when you put those back into the system. Okay, now that that's done, how are you going to compensate this? How can you compensate for this without screwing up all the work that you just did before to design the control? Because that's a lot of what you try to do is you get your ideas of how you want to stabilize your system. You stabilize it, you get the performance that you want, and then when you actually test it, you discover there's some things you didn't consider. And your assumptions are off. When you go back and you try to fix those, you would prefer if you didn't screw up all the other stuff you just did, all right, and that it still worked okay. So this is a lot of what we spend our time doing.
Weird stuff going to screw you up. Going to show up in Simulink, or is it real world phenomenon?
Depends on how carefully you model it in Simulink. If you model a high frequency noise in Simulink, yeah, it'll show up. What we'll do in this problem set, where we tell you, okay, here are the high frequency poles that you ignored. Now deal with them. Right? Now see what happens. Okay. So these are proportional, derivative, integral. We very, very rarely we use proportional alone all the time. Trying to think if I've actually come across a pure derivative control. I think in a voice coil actuator you might use pure derivative control at some point, but maybe not. It's something. It's a pretty rare beast when you use it by itself. Generally, it's proportional plus derivative, proportional plus integral, or proportional plus integral plus derivative control. Usually, this sort of you tune the knobs, but there's definitely a proportional piece to it. Okay, so when we looked at proportional plus derivative control, what we found was I can model this as a 0. So now I have 2 degrees of freedom. I have the gain, and I have the location of the 0. This is because Kp plus Kd over S, oops, that would be integral. Let's try that again. This is Kp plus Kds, looks a lot like Kd times S plus Kp over Kd. Okay? So choosing my proportional gain, my ratio of proportional derivative gain tells me where that 0 is going to be located, and the derivative term, the Kd term, tells me how much gain I crank into the system. Right? As long as I hold this ratio the same, I can crank that up and down as much as I can. All right, so I have 2 degrees of freedom now. And with 2 degrees of freedom, I get much better response than I get with 1 degree of freedom. This still has the problem of amplifying. So this is a high-pass filter. It's a high-pass filter at this frequency. That's the corner frequency. Right? And it's going to also amplify all high-frequency noise. Right? Now, this is because if I take sine omega t, let's do cosine. Right? So I'm going to take cosine omega t. Right? And I'm going to take d dt of cosine omega t is equal to omega t. Right? Sine omega t? Is that right? Negative? What's that? There's no t, that's right. Negative omega. Right? There it is. Okay? As my frequency goes higher, right? This is a derivative function. As I take the derivative of it and crank it up in frequency, that gets bigger and bigger and bigger. Right? And if there's any noise, right, that gets amplified by my frequency. So this is, in MATLAB, a pure 0 works just fine. Okay? Beautiful response. In the real world, it does not. Okay? So one of the things we do, we say, okay, that's great. And PI control, so we'll come back to that. Let's do PI control. PI control is going to be a Kp plus Ki over S, right, which is going to be equal to little algebra Kps plus Ki over S, or Kp S plus Ki over Kp over S. So this one is a pole at the origin and a 0 that I can move around. Okay. So this has the integral quality, which is nice, right? So the integral quality says, hey, that's good. I make sure I go my steady state error is going to go to 0, but I got to be careful about dropping another pole right on the origin because that's going to be destabilizing. Right? So I've got to make sure I haven't done more damage than good by doing this. All right? Yes, I've dropped my steady state error down to 0, but I've paid a price for it. Okay, so now we're going to start looking at our leads and our lags, which are similar to. So let's start with my PD controller. Okay, this has a pure 0 right here. Okay, and we say this has some problems. Okay? The problem that it has, for one, is that I have now no DC gain, which is bad. The second problem I have is this is amplifying high-frequency noise. And so I say, well, okay, I'm going to solve the DC gain problem by moving my 0 off of the origin. Okay? It's still close to a derivative, right? But it acts less and less as a derivative of DC and becomes more and more of a derivative as I go to high frequency, right? Because when I'm evaluating this way away from here, the difference between it being on the origin and slightly off the origin is pretty minuscule, right, as I get far away. So at high frequency, this acts like a pure derivative. At low frequency, it does not. So it allows some DC to pass, which is good. And then I'm going to say, but this is still giving me the problem of amplifying high frequency. So what I'm going to do is I'm going to low-pass filter it by sticking another pole out slightly farther. Okay? So what this is it says, hey, this pole, this is A over S plus A, and I put the A on top of it just so I get a DC gain of 1. Okay? If I look at this and I plot this in the frequency domain, right, here's my corner frequency A, and that's the magnitude, and this is log frequency. Right? So it's going to go and it's going to fall off, and it's got one pole, so it's going to be 20 dB per decade that it falls off. Right? So this is a low-pass filter. This is a high-pass filter. This one, let's call this B. Here's the corner frequency B. This one's going to come up and do that. Okay? So here's the magnitude, log frequency. So combining them, what I get, so B is less than A, is I get something that looks like this. It comes up, it levels off, and then it goes back down again. Right? So I get, this now becomes a bandpass. Right? So I get a good pass in between the two, right? And it falls off on either side. All right? So this is a happy thing. Okay. So this is sort of the justification for. So this, the way I can look at this is I can say, hey, I'm going to take a PD controller, but use add a low pass to it. So I'm going to have KP plus KDS times A over S plus A. Right? And this is going to equal to KP S plus A plus KDAS all over S plus A. And this is going to equal to KP plus AKD times S plus KDA over KP plus KDA, all divided by S plus A. Okay, so this is a lead. All right. And if I look at this in the complex plane, what this means is I have my 0 first, my pull farther down. Okay? And I'll get to why this is called a lead slightly later.
And in a real-world system, that's just equivalent to sticking a filter on your sensor?
Yeah. This is sticking a filter on my sensor and a filter with a low pass, right, on my sensor. Now, the only place I've actually seen pure derivative control work well is when, due to the physics of the problem, you have a direct sensor that measures the derivative of the thing. If you're trying to build a synthetic derivative, either by differencing measurements or by putting an op-amp circuit with a capacitor in it to try to make it take the derivative, what you will get is high frequency noise. Period. That's and so by adding this low pass filter to that, what you say is, take my sensor signal, low pass filter it first, then go ahead and take the derivative of it. Right?
That's common sense.
It is, actually. Surprisingly missing for many engineers who go out and do this. Right? This is one of those funny things where people who take controls classes go out into the real world and they say, oh, I can control this, no problem. I'll stick a derivative controller on there, and they don't understand why the thing just hums. It sits there and it chatters back and forth. And they say, well, but it should work. I put in derivative control. I should be removing energy. How come this thing is still chattering? And so this is one of those things where, yes, it makes perfect common sense, and in practice, it's the way you actually do it. We don't teach this class here, although it's one I would like to teach if I can do it, where you actually build control systems using. So there's a question. The class that I took, we actually did it with op-amps, and trust me, anytime you start looking at compensation that's even a little bit more complicated than this, You're like, okay, I don't want to build that. Yes, much as I want just pure. I want to rearrange my sensors and my actuators such that pure gain gets me there. Right? I can gain stabilize the system because if I have to start building this out of op amps, okay, a first order compensator I can do. Okay, but when I wind up with something like a sixth order Butterworth filter, all right, I get very unhappy trying to build this with an op amp. All right, and because it won't work. Period. I mean, you wind up discovering that, well, it works, it worked at night, but as soon as the sun rose and the temperature in the lab went up slightly, it stopped working again. Things like that. All kinds of things start happening where you're like, what happened? It was working last night at 3 in the morning, I swear. And TAs are scratching their heads and like, yeah, right. So you wind up trying to figure out what you can do with the simplest kind of compensation you can. All right, that gets you there. And, now, the other way to do it is you say, okay, I'm going to use a microcontroller and do it that way. So I'm going to take my sensor, I'm going to put it probably through an analog low-pass filter. All right, I'm going to roll it off through an analog low-pass filter, and then I'm going to shove it into my A to D. And then I'm going to sample it at a fixed uniform sampling rate. And this is actually very important. If you have jitter in your sample rate, your control goes all out of whack. But then I can actually do, by simple multiplications and additions, I can implement any compensator I want. All right, and this is the power of digital control. And it don't drift with temperature. All right, this is a huge power. And I want to make 10,000 of them. I just copy software. I mean, it's great. It really is quite fantastic how much it works and how well it works. And then I can get all kinds of fancy and complicated. It turns out there's numerical instabilities that you run into from round-off error. All right, so there are ways in implementing it that work. In theory, doesn't matter which way you implement it; they all work equally well. In practice, what you discover is oftentimes it depends on whether you have 0.999999 as the coefficient or 0.9999999 will actually make a huge difference in the stability of the thing. All right, and so you start discovering that your round-off errors start cascading and giving you problems, and so you try to implement, double floats in a, double precision in a microcontroller, and you discover that this doesn't work so well. It does work pretty well, even in a microcontroller, if you know what you're doing and you're careful. There's lots and lots of tricks on implementing this as fixed precision to make it go really blindingly fast. It works really well. The advantage of doing it with microcontrollers, in addition to getting, being able to implement fairly complicated compensators easily, is you get the if-then-else statement that you get to work with. All right, which means you can actually switch modes in and out relatively easy. Where doing that in analog electronics is a royal pain. Definitely not worth the trouble. Okay, so essentially a PD controller with a low-pass filter on the sensor output before it goes into my system gives you what we call a lead compensator. All right. Now, if I do the same thing and I say, look, I'm going to have a lag compensator, and so what I'm going to do here is, let me see where I am in my notes here. These are problems that were on the midterm. Definitely not going to give those to you. Because that would be, too easy. All right. So if I take my same argument and I say, well, I'm going to take what was my PI controller and I'm going to move the pole off the origin to the left a little bit. All right. Now what happens? The first thing is I gain back my steady state error. Okay. If it's not on the origin, it's not going to zero. All right. But it's close to the origin, which means it's not big at all. All right. So this gets me DC amplification. All right. So I get lots of gain at DC by putting this in here. All right. But the advantage is, if this one happens to be going this way, right, then I got a little time, right, before I lose it. And depending on how close this one, the zero, is to that one, I can slow this down a lot in how fast it departs. All right. So I've got room to play with here. Okay. And this one we call a lag compensator. And let's see. What do I have here? Those are... Okay, now, another big problem with my lag compensators, or with a pure... So, the problem with this guy, he's still destabilizing, right? Right, I'm still putting a pole near the origin, and it's not as immediately destabilizing as putting a pure integral control on there, but it's still doing it. Right, I'm still putting a pole near the boundary of the do not pass sign, and it's going to pass. So sticking another pole out there is going to cause everything to go to the left. All right, so this is a right. Things are going to go right, which is going to be in general a bad thing. Okay. So now, the other problem that integrators have is that if I have a saturating control, right, so say I do something where I put an input in time, I give it a step in, okay, and the output, in order to do this, is going to do something like, it's going to jump up way here, and it's going to do something like that. So this is U, and this is R. Right? So this is typical system response where I hit this with an infinitely fast step, right? This thing jumps up to infinite and then comes back down, right? And it says, okay, push on the system hard, and as I get close to where I'm going, the output is going to look like something like that, right? So as I'm getting there, it's slowing down how much it's pushing. I overshoot, it corrects the other way, and it comes back down. Okay? Now, this works, okay? But suppose I said, well, in real life, my actuator saturates right about there and there. I can't go any higher than that. Okay? So you say, well, what am I going to do? Well, the easy thing is you say, well, go as big as you can, all right, and rail at my saturation limit. Since I want to give it more U, I can't. What's the next best thing to do? Give it what I can, all right? Now, what will happen is, as it comes back, it'll hold a little longer, because this will slow down a little bit, right? This will go like that. It'll hold a little longer there, and then it'll come back down. Now, here's where life gets dangerous. Okay? If you add integral control to this, all right, while your actuator is saturated, the integral control says, no, put more for you. I've got error. I'm integrating up. I'm still integrating up. Right? And I'm still integrating up even though you can't give me any more actuation. You've given me all you can give, but I said, no, I want more, and I'm accumulating. Right? An integrator is an accumulator. So I'm accumulating this baggage that I'm getting as I'm winding up, such that when under normal conditions I'd start coming down, the integrator says, no, you've still got to push in the other direction. Right? So the integrator will cause you to hold at saturate, right, value longer before it then comes down, which is going to cause the new, I need more colors, cause this guy to keep winding up until, it finally comes down, it's going to start going. You're going to get more overshoot, which implies less damping. Right? So there are ways that people do this. What they use is some logic functions that are called integrator anti-windup. So one of the simplest things you do is you check. And if your actuator is saturated, you don't integrate. Okay? You only integrate while your actuator is not saturated. Right? And this saves a lot of the problem. And there are various issues with integrator windup, and there's lots and lots of literature on how to solve it, none of which are sort of methodologically sound. They're all ad hoc rules. All right? And people have discovered, they work well. All right, so one of those things to be aware of.
So when I want to integrate with saturated, what kind of response will I have then? The middle one?
Right, so it'll have the middle one. So it's saturated, but it's not winding up, so it's not accumulating any baggage. So when it comes back down, you're not destabilizing it less. Right? Now, there are some very, very fancy methods where you can actually deal with a saturating actuator as it's a dual Lagrangian function, and you can actually solve the optimal control problem exactly, even with the saturation, and deal with it. And it's pretty cool, and I don't claim to understand it, but it does work. So, the other piece that's missing in all of this is, all right, let's go back to our standard drawing. All right, so I have this, I have my error, I have my compensator. So in this case, we're going to call it, oops, let's put a B and an A. Let's make this lag. Here's my plant, G of S. Okay, and I'm coming back. So if I look at my E over R, right, this is 1 plus kg S plus B over S plus A, which is equal to S plus A over S plus A plus kg S plus B. And if I take this into steady state, I get that this looks like A over A plus k G of 0 times B. All right, so if A is small relative to B, okay, and what does it mean that A is small relative to B? That means that A is here and B is out there. Right? Then this looks like A over kg dot B, which means that this steady state, A is small, B is big, right? I'm getting very, very close to an integrator, and I'm bringing down my steady state error. Right? So I can bring down my steady state error. Now, if A goes to 0, then sure, I've got a steady state error of 0. Right? But I don't need it to be 0 to get a pretty decent steady state decrease. Okay. So far, so good. Right? Nothing. Ooh, this one's interesting. All right, let's see. I think we're done with this one. Okay. So, now, the interesting thing to remember about all of this is that root locus is only going to give me my transient response. It's not going to tell me much about my tracking error. All right, so that's an important thing to remember. All right, and one of the things I can do, be careful, by the way, about putting zeros in the right half plane. It's a legitimate thing to do, but they're a little squirrely. They're called non-minimum phase zeros, and they make your system respond by going the opposite direction first. So it's it's something that generally you'll do because hey it works. But we'll get there. This is getting into Bodhi. We don't want to go there just yet. Okay. So the question becomes, all right, I need now some type of systematic way to choose compensation. So let's say I have this system, okay? And based on my ideas of where I want my settling time response and what kind of overshoot and everything else, I decide I need my poles there, right? This is the little notch in my, whoops, right? There's my notch, that's where I want them, okay? Now, can I get there with just straight gain? No, right? What happens with the root locus on this guy? Center asymptotes, they take off, they split vertically, and they go 90 degrees. All right, so I cannot move these to there. So the question is, how do I want that spot. How do I get there? Well, let's be a little systematic about it. I'm going to say, look, I know how to measure those two phases. Right? So I'm going to say that, let's say phi1 is equal to, that looks like about 135 degrees. Phi2 looks like about 120 degrees, where I put it. Okay. So if I take a look at this spot, I say that the phase at this point, minus 135, minus 120, plus some unknown phase amount, call it phi question mark, right, is equal to minus 180, right? If the phase at this point added up to 180, I'm on the locus. I know it doesn't, right, because I'm not on the locus. Okay? The question is, what does it add up to? So if I do this, I find that this is going to be minus 225 degrees plus phi question mark is equal to minus 180. All right. So that means that I need to add 75 degrees of phase to my system. 45?
Yeah.
120?
Well, it's
255. That's not 225. There we go. Intermediate step was wrong. Okay. So this says I need to add 75 degrees of phase to get myself on that root locus. Okay. Now, here's where life gets super cool. All right. I've got my original. All right, let's ignore these two for now. I'm going to look just at my lead compensator. My zero, my pole. Okay. So this is A, right? And this is B. No, this is B and this is A. This is S plus B over S plus A. And we're going to put a K in front of there, but we'll deal with the K later. All right? But this is the compensator I'm putting in. Okay? Now, if I go to my point up here, okay, and I evaluate the phase that I get from this zero and this pole, okay, I need to do this over because I'm going to have to do this kind of neatly. Okay. I've got my zero. I've got my pole. I've got my point of interest here. That's where I want the locus to go through. It's so hard to draw straight lines. There we go. All right. This is phi zero. This is phi pole. Okay. The phase that I need from this guy, the phase at this point that I get from these two is going to be phi pole minus phi zero. Okay. So I'm evaluating these two at this point. Sorry, phi zero minus phi pole. All right. The pole is always negative. There we go. Okay? So this is the phase contribution of these two here. Okay? Now, if I look at these angles, okay, let me redraw my horizontal line up here. Okay? And extend this up here. So I'm going to say that phi zero here is the same as phi zero there. Okay. And if I extend this line up, I've got that phi pole here is phi pole there. Which means that that angle right there is phi pole minus phi zero, which is that angle there. Right? So, if I make that equal to 75 degrees, and I go ahead and I drop it on top of this, a branch of the root locus will go right through that point. It has to, because the phase is now 180 degrees at that point.
You can't just put it anywhere.
Actually, this is the interest. This is my degree of freedom. Okay? So as long as I have an internal angle of 75 degrees, all right, then I actually can do this. So let's look at where. So here's this whole thing. So now the internal angle is constrained. Okay, but I can I can move it back and forth. All right, and I can decide where it makes best sense for me to put it. But I guaranteed that the root locus is going to go through this point, regardless of where I slide these two along. But I can slide these two along maintaining the internal angle of 75 degrees. Let's look at the two extremes. Okay, so now there are some that may be better than others. And remember, I'm only guaranteeing that a branch of the root locus goes through there. I'm not telling you where the other branches of the root locus go. See, this is a beginning. It is not a cookbook. Okay, just doing this doesn't solve the problem. It simply gives you a place to start. All right, and then you've got to tweak and iterate and find out where you're going. But let's take a look at this. That was interesting. Huh. Weird. Okay. So if we take a look at this, I'm going to say, look, here's my original two poles. And I wanted to come up to here. Okay. So I'm going to add a 0 and a pole, a 0 and a pole, such that the difference between these two is 75 degrees. Okay? And I can slide these back and forth anywhere I want. So let's do the one where I'm going to slide that 0 all the way to positive infinity. So that angle, the 0 is all the way out there. So that means that 75 degrees down from here, I'm going to get the other pole. Okay? Now, I'm going to draw the root locus for this, and I say, okay, well, what do we got? I've got this one is on here. This one, right, is on here. All right, what's that? The 0 is way, way out here. Can't see it. It's gone. All right. And in fact, that doesn't seem to work. So let's No, but that just worked out that way. All right. Let's go the other way. Let's say I'm going to push the pole all the way to minus infinity. So, and then I'm going to wind up with a 0 that's 75 degrees down from this guy. Okay. Now, what the root locus looks like, these two come together. They're going to come in here. They're going to split, branch, go right through that point, come around back here, and go. Okay. Now, you say, okay, what happens if I bring it in? Okay, because, well, this is now back to my pure derivative type control. Remember, we don't like to add pure zeros, right? That's adding a filter with an infinite roll-off, so that doesn't work too well for us. So you say, okay, no problem. I'm going to do the next one where, so we're here, we want to bring up here, and I'm going to bring in the 0 and pop it right on top of that one. Okay? And then 75 degrees away, I'm going to have that one. Okay? So the root locus here is going to wind up doing that. Right? So I've effectively canceled that one. Right? Now whether it's this one that leaves and hits this one and that one goes to this one is pretty much what's going to happen, or you can sort of ignore that pole 0 actually cancels it, works out so you'll go right through that point. Okay, well, I'm going to keep going. I'm going to keep sort of sliding over. All right, so now I'm going to go, so my original 2, the point I want. I'm going to now move the 0 in between, and 75 degrees away, I'm going to move that one there. Okay? So now I'm going to wind up with those two, and these are going to figure out where the asymptotes are. Yeah, these are going to split and do something like that, right, where that one goes to that one. And I can keep moving this, and they're always going to be, now watch what happens if I get a little feisty, and I say, well, no problem. I've got this one, and I'm going to move the 0 right here, and then 75 degrees later, I'm going to put another pole here. So that one's on. So this one's going to go here. These two are going to do that, right, and eventually go up like that. And I say, okay, well, let's take it one step farther. And so here are my 2. Here's my desired spot. Put this in here, which gets me another one in here, right? These two are still going to meet my point, right? But, yeah, does it happen before or after this one goes the other way? The farther away I move this one, the faster this guy's traveling from here to there, right? And therefore, you know, you got to be careful about this. You have a degree of freedom, right, of where to slide this along, but that degree of freedom isn't unconstrained at all, right? So you still have got a lot of things that are going on. Let's see. Okay, now, what happens in the case of? Let me just make sure where I am here. So all of this is a way to look at this and see where we're going with this. So remember that the root locus is only going to give you the transient response. All right, and if you put your 0 in the right half plane, you can get some very, very, very strange results. So if I do this, and I have a 0 here, and let's do this. Okay, so here's my system. All right, so the root locus on this one, that one goes in. Center of asymptotes is going to be, right there. These two are going to pop up and do something like that. So I look at this and I say, okay, well, I'm going to go through my transfer function, right, and I can get my error over R, and I go ahead and I do my my plot of, and I get an expected value, and I put in a step function to this, and I get something that looks like that, where instead of it being close to 1, it actually goes the other direction because of the 0. So this is one of those things where you get more and more comfortable with it as you start sort of plotting them all out, and you're like, ooh, putting a 0 in the right half plane does strange things, right? And that's one of those things that you're just going to have to get used to. Now, we're going to go back and we're going to look at my my various compensator. All right. So this is one of those things where, let's say I have my system. It's got some unmodeled or in this case, modeled high-frequency oscillatory modes. Okay, and normally the root locus on this is, well, that goes up, that goes down, that doesn't help. Okay, and I say, all right, I'm going to put I decide that I'm okay with the speed of the system. It's fast enough, but it doesn't give me the damping I want. So I'm going to move the point to here. That's where I want it. And I say, all right, fine. I'm going to put I'm going to figure out how much phase I need. Right? So I'm going to add up the phase from here, 90, a little more, add it up, and I'm going to come up with a number, and I'm going to say, okay, I'm going to put down a lead compensator that's going to do this for me. Okay? And I say, all right, and I'm going to put, it's going to wind up with a 0 here, a pole there that adds the right amount of phase. Right? And what's this going to look like now? This one's going to come in. This is going to move the asymptote out something like this, and the way this has worked, these two are going to go through there. They're going to go through the point I've marked and then back up. Okay, so that's the
Question. I'm suddenly no longer believing. Okay, we're doing all this like root locus so that we can go determine our omega p and omega p specifications of our system.
right.
But if our system is hence the maximum, then it proceeds to go back down the opposite direction. I'm beginning to lose faith that we can actually get those values from where our zeros are.
Well, remember that you're looking for the root locus is plotting the motion, right? The locus of points, a closed loop system as a function of some gain.
Right.
Okay. So by putting down this lead compensation, I can force the locus to go through any point I want to.
But aren't those? But once we go choose a gain for our system,
Yeah.
that determines the set of zeros and poles for our.
That determines the closed loop response. Correct. But remember that root locus is only giving you transient response specs. Okay, rise time, settling time, how fast it's moving. It's not giving you anything about tracking specs. For tracking specs, we need Bodhi, which we haven't done yet. All right. So the way we get around having no tracking specs whatsoever is we force you to look at a steady state error, kind of thing. Okay. So I can move this around. I can put this. I can put this through here, and this works. Great. Okay. I've got my spec. I'm doing all right. As I said, if I move this 0 into the right half plane, all right, then strange things start to happen. All right. So from the math, it's all just fine. But if you actually go all the way through and do a step response to it, you will get something very unlike what you think you ought to be getting. Right? So just the right half plane zeros, they're referred to as non-minimum phase zeros. And they're definitely something to stay away from. Okay, so they're a bit bizarre. However, I can get, as I said, I can get my my system to go through this point, all right, and I'm okay, and I'm doing fine, all right, as long as I do this. The problem comes when you say, all right, what happens if I look at a slightly more complicated system? So I've got R. It's not much more complicated, but just slightly more. I've got some compensator K, and this is not just a gain K, but K of S. I come in, I have a disturbance that comes from the world. I have my plant, my output Y. I'm going to leave it as a perfect sensor, but say I've got some noise in it, and this feeds through. Okay? So now, if I say, look, my Y over V looks like kg over 1 plus kg. My Y over my disturbance looks like G over 1 plus kg. And my tracking response looks like kg over 1 plus kg. Now, you'll notice here that my noise response and my tracking response, bummer, are the same. Okay? So you say, well, this kind of really sucks. Because what this is telling me is that as much as I want my system to follow my input, right, it's also going to follow any noise on my sensor. Because specifically, my sensor is telling me where my system is. And so it's going to track that with perfect tracking gain. All right? What I've worked so hard to make my system slew around and point where I want it to point, it says, well, if you get an error in your sensor, it's going to follow that sensor, right? Because that, yeah. Well, so now the question is, what do I want to do? So I can reason and say, well, wait a minute. I'm going to work very hard at the frequencies at which I am concerned. Okay? I am probably not going to track this. I'm not going to want my system to track at as high a frequency as the noise is going to be bothersome on. In other words, I can work pretty hard at making this fairly good at DC, all right? But it's going to have some high frequency noise on it, right? Because as I'm trying to get my sensor to track to give me data faster and faster, it's going to have some issues. All right, all sort of real implementable sensors will start breaking down at higher frequencies. All right, and so I can say, well, okay, I'm going to plot the magnitude of my loop gain, GK, right? And I want to plot it versus my frequency. Okay? And what I can say is, look, if GK or KG is big, all right, that means that I'm really good at rejecting disturbance. Okay? So at low frequencies, all right, I want disturbance rejection. All right, so I want high gain at low frequency. In other words, I want this to be 1 at low frequencies. So when I tell it to go 15 degrees to the left, it goes 15 degrees to the left. All right? At the same time, I want, so this is also tracking, right? Down here. Now, at the same time, way up here at high frequency, I want KG to be small. Why do I want it to be small? I want it to be small because I want to attenuate my sensitivity to noise at high frequencies, because I know I'm going to get noise at high frequency. Right? So I say, well, look, I know I'm not going to make this thing I'm not going to slew my telescope at 5 kilohertz. It's just not going to happen, right? Because mechanically it can't move that fast. Right? So what I want is attenuation at high frequency, which gives me not only noise rejection, which is good, also plant uncertainty. It's fairly easy for me to model the sort of first fundamental modes of the plant that are at lower frequency. When I start getting into sort of how the telescope is flexing in its mounts, those are starting to get hard to model. And so I'm going to take my best guess, but the truth is I might be wrong. And those are all going to show up at higher and higher frequency. So the fact of the matter is, if I just slam them all down at high frequency, it doesn't really matter if I'm wrong or not. They're gone. The slope at which I come through here gives me my stability, as it turns out. Right? And we will get to that once we there's a way in which this decreases that buys me stability that we'll get to once we get to Bodhi. All right? But the fact is, I want lots of gain at low frequency, which gives me good tracking performance and good disturbance rejection. I want attenuation at high frequency because that gives me noise rejection and an insensitivity to plant uncertainty. All right? So this is, now we start doing kind of fun stuff. And we say, well, where are we going to do this? Well, we're going to do this by a lag at low frequency gets me low frequency gain, but it rolls off at high frequency. Okay? I use a lead to get me my stability that I need in here. Okay? And then I add low pass filters, right, which just look like excess poles down here to knock down the gain at high frequency. All right? So this is a typical Bodie type argument, and we're going to get much, much, much more in depth on how we do this. All right. So, but I wanted to bring you one last piece of compensation. All right. Let's see. Here's a more interesting one. Let's see. Okay. So let's say I've got a system that looks like 2 poles and all right. Let me before I do this one, which is it's something I want to do, but hold on a second. All right. Before I do this one, let's be sure there's one thing I want to make sure of. The piece of information missing from all of these, of course, is how fast things move along their branches with loci. Okay. So if I've got, so I had my compensator I designed, and it worked well for this. And I've drawn it really tiny in here because then I've gone along and I said, well, when I look back, it turns out there are these very high frequency unmodeled dynamics I didn't know about. Okay, and what I want to do is I designed my compensator to work on this, and I have to be careful about these guys because these guys can go unstable. All right. But the interesting thing to note, first of all, is how fast do these guys move with gain? Okay. One of the things to realize, what is my gain up here? It's going to be K. Well, so let's see. If I look at what the magnitude of it is, there's going to be a length to all of these guys, and I'm going to be evaluating at a little pole. Let's say these two move like that. I'm going to be evaluating this at a little distance away from this pole. Okay, so let's call that distance from there to there. Let's call that Lx. Right. So my gain, or the magnitude of the function, the magnitude of g, or gk in this case. So the magnitude of gk evaluated at this point, right, on the locus, is going to be Lx times the sum, or actually the product rather, of the L to all of the other poles divided by the product of all the zeros. Right? Did I get that right? Or do I have it upside down? I have it upside down. Right? Those are zeros, those are poles, and this is 1 over Lx. There we go. Yeah.
So we're changing our gain frequency?
No, this is just looking at a point on the root locus that's near this one pole that's far away from all the others. Okay? As I move along back and forth on this line, how much do these guys change? Not much at all. Right? In fact, I can call those more or less a constant. Let's call it C because I'm using K. Right? Which means that my gain that puts me on here, which is 1 over the magnitude, is going to be pretty close to Lx. Right? So the gain, these guys may be moving quite quick relative to this guy. Right? Because it gets scaled by these, right, by this constant, and then it moves away, right? So it's one of those things where you got to be a little bit careful, right? But okay, so which brings us to, remember when we did the table with the little camera on it, and we showed what happened if we had our different things. So we had our system, which looked like essentially there were 2 poles on here. Right? And we said we wanted to bring it into a spot that looks like, right? We had this, we had that. These were the places I wanted to move it to. And I said, okay, well, in order to do this one, we're going to put a lead on this guy. He's going to come shooting in. They're going to go out like that, and they're going to cross right through my point where I'm happy. Okay, so here's my system. And then we came back along and we said, well, if I draw those at the scale 1, 2, like that, way out here, there was this other set of poles you didn't know about. Okay, bummer. Right? High frequency stuff, vibration modes that you never bothered to check because they're way above the frequency of interest where you plan to slew the system, but you're exciting them. Okay, because when I do this compensation now, right? So now what does my root locus look like? This part, well, this part's still on the locus, right? Except that now instead of having 2 asymptotes, right, I got 4, right? Which means these guys are still going to probably go. I probably haven't actually altered a whole lot the point at which they go through my lead because these are so far away. They don't have that much of an effect. So these two split and go along, and probably where I had them, they're fine. The problem is these guys are doing something like that, and that is bad. Right? So the compensator I designed to fix my system just got broken. Right? Which brings us, so we did lead, we did lag, which brings us to the last one of interest, okay, which is the notch. Okay, so I don't want to mess with all of this, but I got to do something about these up here. Okay? So what do? I say, look, I'm going to put 2 zeros and 2 poles. Okay? So the notch looks like an s squared plus 2 zeta omega naught s plus omega naught squared divided by s squared plus 2 omega naught s plus omega naught squared. Okay? This is the notch. Right? The reason, by the way, this is called a notch, we have to go to Bodhi to do this, but if I plot the magnitude of my notch versus log omega at omega 0, it looks like a notch. Right? That's why it's called a notch. All right? So this is a notch filter, and what it is, or oftentimes you'll hear it called a band stop filter, right, as opposed to a band pass. Now, what's going to happen? Why is this so important? Okay. Remember that the zeros suck on the poles, right? And they slow them down. So by putting the 0 nearby, I can slow down the rate at which this guy takes off and goes outside. All right. So I can just sort of put him near and think of the 0 as a gravitational well, all right? And that this guy sort of needs to climb out of that well to go. It's going to slow down. You can also think of these as sort of charged particles. All right. So the x's are attracted to the o's, so they're going to do that. But it also allows me to do something else. By being clever about where I put this 0, I can alter the departure angle. Right? Now I've added 2 poles and 2 zeros. Right? So what happens to the asymptotes? Nothing. Right? I mean, I'm moving the center of the asymptotes, but the angles of them don't change. They're still going. Right? But the question is, which way are they going? By moving this carefully around, I can change this departure angle to go from here, where it departs straight into the right half plane, to here, where now this guy's going to button hook around to this one, and these guys are going to take off and go, or these guys are going to turn around, go that way, and these guys will do something like that. All right. But for small gain, I'm going to look an awful lot like I had before, and this one's going to move in next to that 0 and get attenuated. All right. So the notch filter is interesting, okay, in that what you generally use the notch for is, you've discovered that you have these unmodeled dynamics way up there, and I'm just going to drop a notch right on top of it and knock that peak down. Okay, that's what I'm doing. Okay, and it'll make much more sense in the Bodhi style when we go there. But nonetheless, in the root locus, they're very important because I can manipulate the departure angle, right? And I can manipulate the rate at which it departs, right? By doing this. This is reasonably easy to build. Okay, it's easy enough in real life to actually build a notch and put it in there. So it's implementable, which is nice. And again, as long as the frequencies are roughly of the same magnitude, okay, then this doesn't really affect the stuff on the inside a whole lot. Right? For, to first order, this hasn't changed, right? So it's sort of a scale issue, right? As you go in, right, this looks more or less the same. It's going to turn around and go out later as you really crank up the gain. But as long as your gains are small, it doesn't matter. Yeah.
Why did the X's originally go to the hole and that one the ones near the origin go along the asymptote the first time around?
Well, okay, so the first time around we had 1, 2 here. We put this like this.
Right.
Okay? So the root locus on this is that this pole, that's the part on the real axis. The asymptote is here, right? And plus or minus 90 degrees. And this goes, these are doing something like that. Okay? And we picked our spot so that this is where the closed loop poles show up. We pick our gain K to get us there. Okay? And we're doing all right. Okay? Now, when I add the other 2 poles up here that are way out here, right? The asymptotes are no longer there. The asymptotes are now there.
Okay. I'm sorry, I missed that bit.
Right? So, because I added 2 more poles. So I changed the asymptotes. Okay? Got it. Yeah.
If the high frequency poles are way higher than anything else in the system,
Hmm?
how does a notch help you where
Just a low pass. Okay. So, I have something that looks like this. Okay, and I've got, I don't know, let's keep with the system we had. So I had 1, 2, and I had that compensation. Okay. So, I want to roll this off. So a notch says add that. Okay. This is what a notch does to me. Okay. And by where exactly I sort of put this, I can manipulate the departure angle, and that's the real key, is I can manipulate the departure angle. All right. Now, if I just say, all right, I'm just going to low pass this so it attenuates, and I say, well, let's see, let me roll this off by adding 2 more poles here. Okay, that's what a low pass is. Okay. Now what's the root locus do? Okay. Let's draw it. Okay. So by adding 2, those are still there. Right. One of these is going there. I now have 1, 2, 3, 4, 5, 6, 7 minus 1, 6. Right. I got 6, which is divide 360 by 6. So I've got, right, did I get that right? That's 8. All right, no problem. There we go. So I really want to be aggressive at rolling this off. Right? Second order low pass. All right, fourth order low pass. Right? So I really want to get aggressive with this, right, and roll it off. All right. So the problem is all of these guys are going to end up on the root on one of the asymptotes. All right, and so I got to be very careful when I do this. So this is going to mean that I'm going to have a very narrow region of this. While it works to attenuate these guys, is screwing around with what happens at DC.
How do you explain that intuitively?
Well, I explain it with the frequency argument, right? Which is that adding these guys, right, is pumping up my gain at is removing phase that I need for stability, right? So we look at the top, we look at the bottom, and this part in between where it runs down gives me a stability argument, the slope of this. So by doing this, I'm altering the slope rather drastically, which is altering my stability. Right? A notch, by having 2 poles and 2 zeros, doesn't do much to the phase. Right? It leaves it alone for the most part, except in the vicinity of the notch. Right? So this kind of compensation works. Right? You just have to be, what you actually have to do with these is get these to move. So what you would do here, you have my 1, 2, you have my little thing here, these guys way up here. I probably would roll these off out here. Right? So I'm leaving this alone, which from in here I can more or less ignore all these things that are very far away. They're going to have an effect, but to first order it's going to look the same in the near vicinity of this, and then it's going to go out. Right, and as soon as I try to crank up the gain, then they're all going to go unstable.
So it's okay if the high frequencies are really high.
Yeah.
Just
You want to sort of separate your frequencies if you can. Sort of like, remember from sort of driver's ed, you separate your hazards kind of thing where you're supposed to. Do you guys never got that? Separate? No. Okay. All right.
I have a question.
Yeah.
If PD control allows you to put a 0 wherever you want on the real axis,
Mm-hmm.
could you chain a few of those together and just put like 3 zeros way out to the left?
Yeah, you can gang them. So
That
what?
will suck the high frequency poles over to the real axis.
Right, but then you can do that. Okay, but now you're still amplifying high frequency noise. All right. So remember that there's problems with pure derivative.
But I thought those poles were the high frequency noise, and you've already modeled them.
No, those are the high frequency dynamics. The noise comes in from your sensors. All right. So that's the other one. Let's see. I've got a. Let's see. Here's a plant. How are we doing on time? I haven't done a plant in a while. We got 5 s plus 2 over s plus 1 squared times s plus 10. Okay. So here I've got so I've got this one at minus 10. All right, this one at 2, and 2 of these guys right here. All right, so the root locus is, all right, that comes into that. The center of asymptotes is about right there. All right, so what is the center of asymptotes? All right, some of the poles I've got a minus 10 plus,
minus 5.
right, so the center of the asymptotes is minus 5?
Yeah, because the 2 poles cancel out the 1, 0.
Yeah, okay. So let's just do it. Minus 10 minus 2 minus 2, right, that's rather minus 2. Minus 2 plus 2 divided by 2, so minus 5. So right there at minus 5. All right, so these two are going to go off like that. Okay? So now I say, okay, great. I want my gain at, I want to pick my 2 points, my dominant poles, at 5 plus or minus 5j. All right, so how do I pick, what do I want to do? Right? Well, first of all, how do I calculate this gain? Right, what's K to get me there?
You mean negative 5 plus minus 5 zeros?
Yeah,
Well,
minus 5.
Isn't that impossible? Because on the asymptote, you just can't reach by definition.
Okay, but let's say it's close enough.
Okay.
All right. So I want to know at the gain that would put me there, I'm going to be pretty damn close to it, right? So
Depends on how big that curve is.
right. Well, actually, this curve is going to go roughly like that, right? Because it's going to orbit around these guys and then take off. All right. So the question is, I'm going to be close to that, but I want to know rough gain that gets me in that vicinity. Okay. How do I do it?
Transfer function.
You know, I have the transfer function, but I also have these, right?
Right.
Right. So what's the magnitude of the function? So k times, let's call this L1, let's call that L2, let's call that L3, right? So the distances to these 2 poles, the distances to that 0, the distance to that. So what do I have? I have k times L2, right, the distance to 0, divided by L1 squared L3 equals 1. Yes. What did I forget? What am I missing? Oh yeah. Well, it's got a DC component to it. Oops. All right. There. All right. So calculate this out, and I get K approximately equal to 10. All right, to get me there.
Did we just measure L1, L2, and L3?
Yeah. You measure L1 and L2, or in this case, I solve it trigonometrically, right? This is 5, right, that height, and that's 4, right? 4, 5, that one, I can solve this one exactly, right? Not a big problem, all right? Let's see, for another one, let's do, I've got, let's see, G is 1 over S squared plus 2S plus 2. All right. And I want to put a, let's see, what do I have here? What was I doing with this one? Oh. All right. So where's this going to give me my my roots at? Anyone? Come on, this isn't that hard to factor. Thank you. I know it's a nice day out. Everyone would rather be somewhere else. But, all right. So let's say I'm going to say, all right, for K in this case, I'm going to do S plus 3 over S. Right? So S plus 3 over S is going to give me that. Okay? And I want to know two things. First of all, let's figure out what the root locus does when I do this. Now, I put in the, so I put this as PI control. Right? I kill the steady state error. There is no steady state error in this. Right? But I've paid a price, and the price I pay is the root locus. Right? So this goes here. Adding the 0 in moves the asymptotes to the right. Right? That 0 looks like a pull that way as far as the asymptote balance goes. So it's moving the asymptote line. The farther out I put that 0, the farther the asymptote goes, which unfortunately means that these guys are going to that asymptote. Right? Now, we do the departure angle of these guys, and so take a quick look. Right? That's 135 degrees. That's 90 degrees. That's, which one is that? Is that 26 degrees? Yeah. All right. So I do, minus phi d, right? Minus 135 minus 90 plus 26 equals minus 180. So I get that phi d is equal to minus 18 degrees. All right. So this one departs like that and winds up going here. Now, I say, okay, I want to know, at what point does it go over? Right? When it goes unstable. Right? So, to do that, do what? How am I going to find it?
In terms of K or JMA?
I want to know at what K I cross the j-omega axis.
Do trig.
You want to do trig for this one? All right. I was going to do it with Ralph. Since I have the answer written down, Ralph, I'll leave it. I'll leave it for you to do it for trig later. All right. Now, what's that?
So at this point, using that the determinant Ralph method is easier than just doing trigonometrically?
Depends on, if the angles are easy. This one is actually probably reasonably work outable from.
We're actually going to have to go sit down and actually do some math at this point. Exercise probably.
You're going to have to do some math either way.
Well, I
right.
mean, not just in
Yeah. So.
Drawing math.
if we do route, we need 1 plus kg, right? I need delta of s, right? Is 1 plus kg is equal to 1 plus k s plus 3 over s squared plus 2s plus 2, which winds up with s cubed plus 2s squared plus k plus 2s rather, plus 3k equals 0. And so I do my Routh array, and I've got 1, k plus 2, 0, 2, 3, 0. And I say, okay, well, this is going to be, the next one is going to be 3 minus 2k plus 2 divided by 2, which winds up at 4 minus k over 2. And then that's 0. And then that last term right there is going to wind up being 3k. Okay? So these two bounds. What's that? Oh, because this one is not 2, but this one is rather 3k. That's why. All right, so what do the limits on that come out to be? That means that I've got 0 is less than k, right? Is less than, so the reason it's got to be 0 is because if I do the 0 angle root locus, right? 0 angle root locus, that's on the locus. As soon as k goes negative, that one's out of there, right? So I know there's the one bound, right? And that shows up right here, right? The other bound says that k is less than 4, right? So this at k equals 4, this goes right through. All right, that's all we've got. I will see you guys all tomorrow at 6. We'll go over the practice midterm, and we'll take it from there.
Question.
Yeah.
One we calculate by taking the determinant of that and multiplying by
And dividing by that.
Okay.
Yeah.
So 1 over that. Okay.
Yeah.
Okay. And for this one, we did that one. This one?
Yep. No.
That.
So it's the determinant. So to go over routes again,
Yeah.
right? What do I have? Let me just write it up, and we'll do this. So I had s cubed plus 2s squared plus k plus 2s plus 3k equals 0. Okay. So the Routh array starts with 1 for that one, k plus 2. All right. Skip it over the next one. All right. So you can put a 0 down there. 2, 3k, 0. So for this one, I want negative the determinant of 1, 3k, k plus 2, 2 divided by 2. Right? So that's 3k minus 2k plus 2 divided by 2. Turns out to be 4 minus 2, or 4 minus k rather, over 2. And this one, so for this one, I'm going to do the determinant so for this spot right here, I'm taking the determinant of minus the determinant of 1, 2, 0, 0 divided by 2, so that's a 0.
Okay.
Right, because it's this and that column. Okay. So now, I ignore this one.
This one was just that one, right?
Right, so this one's this one. You always keep the first column,
And then
it just moves, right? So now I'm going to take, for this point right here, I want minus the determinant of 2, 3k, 4 minus k over 2, 0, divided by 4 minus k over 2.
Always remember the minus sign.
Always remember the minus sign.
Okay.
Okay, so therefore, well, that's just
We just moved down one.
3k.
So that one just was that block.
Right, so now you're using this block. That's the first one.
Yeah.
Right, the next one would be skip this column and use that block.
Specific.
Okay?
Sorry, it's just
No problem.
just really confusing.
Good. That's why we want you to ask.
Edible food. No. What is it? Books, movies, and a bookcase. And a book. Not that book.
All right, let's stop this.